practical. Okay, so acids and bases. All right, so we're going to delve into acids and bases like you've never delved into anything before. Okay, so acids and bases are defined in terms of Lowry-Bronsted. I think you actually should have two little dots on the O of Bronsted. Okay, so there are other models. There's an Arrhenius model, Arrhenius. Oh gosh, I can't remember how to spell it. But there is an Arrhenius model, which we don't do in IB. The GDE will have it. So you'll see it in some of the textbooks. There is an Arrhenius model. But we only do one of the models. We only look at what an acid is and what a base is based on Lowry-Bronsted model. Okay, so that's the one we're working with. And it's very, very easy. And this is exactly what the definition of an acid is. An acid is a proton donor. Okay. Now, this section, acids and bases, is exactly opposite to electrochemistry. And the reason is because in electrochemistry, it's all about the electrons moving. And in acids and bases, it's all about the protons. Now, let's just think about it. What do I mean by protons? They don't move, right? Well, remember you have a little atom called hydrogen. Okay, so this is hydrogen. Okay, and what hydrogen has is it has one electron and one proton. Okay, and look, there are some hydrogen atoms that have a neutron as well, but most of them don't. Okay, so what happens is that if that electron goes away in terms of bonding or something happens and it moves, then what's going to happen is that you're going to just land up with a proton. So a charged hydrogen atom is just a proton, which means it is just a proton. Okay, so when we're talking about protons, we are actually talking about a hydrogen atom that is charged. So we're talking about a hydrogen cation. Okay, and so that's what we're looking at here. Okay, so according to Lowry-Bronsted, an acid will donate a proton. Now, if you think about it, if we look at all these acids, there are hydrogens in all of these acids. You might have the same idea, well, there's hydrogens in bases. But the thing is, the hydrogen in bases is actually forms part of a hydroxide. Okay, most of the time. Okay, the exception to the rule, yes, chemistry and exceptions, would be ammonia. Okay, ammonia has an NH3, but it is a base. Okay, so please don't get that one confused. It is the one exception that we look at. Okay, so an acid is a proton donor. So an acid gives a proton. In other words, an acid gives a hydrogen. Okay, or a charged hydrogen. And the base accepts it. As simple as that. That is what an acid and a base is. An acid donates protons and a base accepts the protons. Okay, so over here, for example, let's take a look what happens here. Now, this is what really happens, is that we can have an acid. We know HCl is an acid. Well, it's a gas until you put it in water. Okay, and when you put this gas, HCl, into water, okay, it donates its hydrogen to water. And look what water becomes. Let me just circle that and circle that. It goes from water to being a hydronium ion. This is a new ion for you. Hydronium. Okay, it's a hydronium ion. Okay, H3O plus. Okay, it has accepted that hydrogen over here, and the whole thing has become positively charged because water was neutral and then it gained a proton. Okay, HCl was neutral, but then it lost a proton, and so it lost its hydrogen and it just became Cl minus. Okay, and that's what happens in water. Okay, now when a base comes, now this is ammonia. Ammonia is a base, and the way we know this is because when we put ammonia into water, the water donates its hydrogen. Okay, so in this case, the water actually acts like the acid. In this case, the water acted like a base because it accepted it. And here it acts like an acid because it donates it. And look what we make now. This is the important ion over here, is a hydroxide. Okay, and all bases when put in water make hydroxides, and all acids when put in water make hydronium ions. And it's those ions that give the characteristics of acids and bases. Okay, the more of those we have, the stronger it is. Okay, so now you can see, oh, wait a minute, water's acting like a base over here and an acid over here. Okay, that's just, it's like a very fake friend that behaves differently with different friends. Okay, so you've got water acting like an acid when they're with a base, and here it's acting like an acid, a base when it's with an acid. Okay, so they change how they react depending on who they're with. Okay, who they're reacting with. So it says, notice that water can act like an acid or a base depending on what it reacts with. This type of substance is known as an ampholyte and is said to be amphiprotic or amphoteric. Okay, you don't have to use amphoteric. You can use one of those or say it is an ampholyte. So it's called an ampholyte and it is said to be amphiprotic. Okay, so I think that's the noun and that's the verb or whatever. Okay, a substance that can act as either an acid or a base is known as that. It's not only water. There are other substances that can act as a proton donor or a proton acceptor. Okay, now let's take a look at some of the acids now. Okay, so let's take a look at HCl. So the hydrochloric acid, where if we had to break it up, it could be broken up into a hydrogen ion and a chloride ion. Okay, how many? You see, we only have one hydrogen ion over here when it is put in water. Okay, because that's what happens. This is the first step, because the very next step is that it then bonds to the water and becomes a hydronium. But so it has to first break up from the chlorine. Okay, then we have sulfuric acid. Sulfuric acid has two hydrogens. So it leaves one of the hydrogens, or one of the protons leaves, leaving you with one proton there and a negative ion, okay, and a negatively charged particle, I suppose. And then that one loses another hydrogen, and so you land up with just a sulfate without any hydrogens. And you see here we have two hydrogens, and each one of those hydrogen ions can then form a hydronium with water. Here we have phosphoric acid. Now we have three hydrogens, and so it can go in steps so that eventually you land up with three hydrogen ions with the phosphate, and each one of those hydrogen ions will then bond with water, making a hydronium ion. Okay, so sometimes acids can donate more than one proton. So a monoprotic, one proton, a diprotic, two protons, triprotic, three protons. But you can get polyprotic, just like polynomials. Polyprotic means more than one. Okay, so you can refer to polyprotic for sulfuric acid and for phosphoric acid. Okay, they are polyprotic. If you want to be specific, you can say that is diprotic and that is triprotic. Okay, all right, so that's some of the theory done. Let's take a look here. So, girls, these acids and bases have been specifically given to you to learn. Okay, so they are in the SAGS document. They have been listed, which means you need to know them. Okay, you also can be told, given a new acid and a new base, and be told about it so that you can deduce whether it is weak or strong. Okay, so I will teach you later on how you know the difference between weak and strong. Okay, so they can actually give you other acids and bases, but they will give you enough information so that you can figure out if it's strong or weak. Okay, so the strong acids that you need to learn are strong. Just know these. Okay, hydrochloric, nitric, and sulfuric, we consider them as strong. The weak acids are your ethanoic acid. Please learn the formula, H3COOH, also known as acetic acid. Acetic acid is an old name for it based on an older organic chemistry naming system before the IUPAC came. So acetic acid, everyday life we call it vinegar, and other carboxylic acids. Okay, so other carboxylic acids in organic chemistry are considered as weak. These are our only strong ones. Okay, hydrogen or hydrofluoric acid, phosphoric acid, carbonic acid, sulfurous acid. Please note the difference between sulfuric and sulfurous. Sulfurous has 3 oxygens. It's made with it's actually made with a sulfite. A sulfite, and the ic acid is made with a sulfate. Okay, so actually when you've got an 8 ending of a polyatomic ion, it actually becomes an ic acid. So this is actually a nitrate, and it will become a nitric acid. Whereas here we have a sulfite, and it will become a nitrous acid. The same would happen if you had a nitrite. It would become a nitrous acid. Sulfurous acid is actually acid rain. So we know it's weak because it doesn't eat holes through everything at once. Okay, it slowly erodes things. And then we have oxalic acid. So this is just 2 of these molecules, and this is also a organic acid. Okay, then you look at your bases. So we're looking at hydroxide. So remember, hydroxide is an OH minus. So we're looking at any hydroxide that is bonded to any of the group 1 metals. Okay, so sodium, potassium, lithium, all of those are then considered as strong. So hydroxides with metals of group 1. Okay, and then everything else we are going to consider as weak. So ammonia, weak. Metal carbonates. So a carbonate is like CO3, and a metal carbonate, let's think, so sodium. Let's go sodium. I think that's sodium carbonate. And so that would be considered weak. Just notice that there is carbonic acid in there as well, which is actually also a weak acid. So be careful. There's a carbonate over here, but it's bonded with hydrogen. And there's a carbonate here, but it's bonded with a metal. So just be aware of that. Okay, and then hydrogen carbonates, obviously, except for carbonic acids. Okay, so be aware of that. I think it's also metal hydrogen carbonates, actually, like hydrogen carbonates. So like if we've made sodium hydrogen carbonate, it's that. Okay, so it doesn't mean hydrogen and carbonate like there. It means metal hydrogen carbonates. Okay, does that make sense? Okay, so acids and bases in water. Very, very, very important. Let me just move this out the way. Okay, so acids can ionize. I have italicized the word ionize, okay, because it is different to the word that we use for bases, dissociate. Now, I want you to think about ionized as you are making it into an ion. Now, technically, if you have a look here, you could see it's all nonmetals, okay? And I want you to think of them as being covalently bonded, okay? When things are covalently bonded, it's not, electrons have not been moved, okay? So they are molecules, all right? So what happens when it enters water is that water, when it's in water, it actually forms ions where it shouldn't have, okay? But it does. And it ionizes. It makes it into ions, okay? Here they're covalently bonded. They're just sharing electrons. And when they're put in water, they are then ionized in water. And it is a reversible process. Oh, are you holding your hand over your face? Because yes, that means we can do equilibrium in acids and bases because they are reversible. Okay, so ionization is the reaction of a molecular substance, okay, like a covalently bonded sulfuric acid with water to produce ions. Sorry, I'm off screen. Okay, with water to produce ions. Reaction, a molecular substance, that means it is covalently bonded. Okay, which doesn't, if it breaks up, it doesn't normally create ions, okay, because it's covalent. They're sharing electrons. Think about sugar, okay? Sugar, when you dissolve it in water, it doesn't break up into ions. It just breaks up into its molecules, okay? And so it doesn't form its ions, not like this. Okay, so this is what sets acids and bases apart from other substances. Okay, so sulfuric acid and water. So it's forming ions. So let's consider what's going on here. Which one do you think is the acid? Okay, well, the one that we know is an acid because we were told that one's going to be an acid. So that one is going to donate a proton to the other reactant. Okay, this is the acid and this is the base. Okay, the base is going to accept it. So what am I left with? I'm left with one hydrogen and an SO4 that is 1 negative. You can go straight into the next step, which just gives you a sulfate. Okay, but I'm going to do this in 2 steps. Okay. Oh, maybe I shouldn't. Oh, okay, it's fine. We will eventually get through everything. So, and then we land up with a hydronium ion, and that is what makes this an acid. The hydronium ions are the things that say, I'm sour, I'm going to burn a hole through your face. Okay. Now it will happen again. So you're actually going to happen, it's actually going to happen again here, where the hydrogen, actually in this situation now, either one of them can donate it back, because remember, this is a reversible reaction. So this one now has a spare hydrogen, and so it can go, all right, well, take that one back, seeing as you negative, and then it goes back to this. So there's the reversible reaction. But also remember, this happens twice, and so you land up with 2 of those. Okay. I will show you later on how you do the steps. Okay, so over here, nitric acid is the acid, and again, this is going to be the acid, this is going to be the base, and you're going to land up with a nitrate plus H3O plus. Okay, and there we have our ammonium. Okay, now when you put a base in water, now let's look at a base. There's a metal, and there's a hydroxide, a non-metal. And so what has happened is that it's been ionically bonded. Okay, they are ions already to begin with. And so when they go into water, they dissociate. They just break up. Okay, there were ions before, or when they were bonded. When they get put in water, they just move apart. It's not like these that were not ions. They were molecules. And when they were in water, they were forced to become ions. All right. Now this one, they are ions, and when they get dropped in water, they just break apart. And they are still ions. They've just dissociated with each other. Okay. So dissociation, the splitting of an ionic compound into its ions. All right. Acids ionize, bases dissociate. So let's just take a look here. So what happens is, this just happens. They break up. They're still water. Okay, so they just break up. And these ones break up. Okay, ammonia is a little different, but we'll talk about ammonia another time. Okay, and they just break up into their ions. So you've got water with these ions floating around it. Where here, water was also a molecular substance, and it also became an ion. All right, I hope that makes sense. Okay, then we're going to look at conjugate acid-base pairs. Okay, and this is what your task is on today. It's really, really quick, and please don't stress about it. It's only 10 marks, and I think you'll be fine. Okay, so, and you can start it when you feel you're ready for it, okay? So, but I would like you to finish it within an hour and a half, please. I know. So this video, I don't think it'll take too long. So I think this is probably going to be half an hour. Then you can maybe work on some yourself for half an hour, and then you do the other one for half an hour. Okay, the task for half an hour. It's really not a big deal. Okay, so the reactants and products in acid-base reactions can be paired into conjugate acid-base pairs. Strong acids form weak bases once it donates its protons. Similarly, strong bases form weak conjugate acids once it has accepted protons. So I'm going to go through these, and then I'll do these with you, and then you can try that exercise. So first thing I want you to do, identify the acid and identify the base. Okay, and you can have a look at the protons. Okay, the products, and you can see, okay, well, I see water changed to that. So that means that water gained a hydrogen, which means that water was the acceptor, which means water was the base. So make it a base. We know HCl is the acid. Okay, now when HCl then donates its hydrogen, it becomes Cl minus. All right, does that make sense? And there's the pair. Before it's donated, after it's donated. Now it actually has become a base. Look at that, it's got no more hydrogens to donate. So it can only accept hydrogens again. Remember, this is reversible. So it could actually take its hydrogen back and form that again. Okay, so, and in staying with Lowry-Bronsted, that means that this will be the base because it will accept the hydrogen. Okay, so this one lost its hydrogen, this one gains the hydrogen. Okay, and so on this side, this has become the base, and this has become the acid. Girls, it will always be acid to a base and a base to an acid. All right, so where's the conjugate acid-base pair? So the acid to that one base, and the base to that one, that side's acid. And you can see, how did they change? Water changed from H2O before it accepted a hydrogen to H3O plus after it accepted a hydrogen. And so they are paired. This one was the base because it accepted. This one's the acid because it can donate now. All right, and there's your pair. Let's take a look at this one. Okay, this one, let's just see before we look. Ammonia has gained another hydrogen. It went from H3 to H4, which means this is the base, which means that one is automatically the acid. Okay, this one and this one have paired up. This is before it has accepted, this is after it has accepted. So this was the base and it has become an acid, and the same with this one. This one now acted as an acid, the water acted as an acid, and it now acts as a base. Okay, because it can actually accept that hydrogen back. All right, here's an ammonium. Okay, so let's take a look at this one. Girls, this carbonate doesn't have any hydrogens to donate, so it can't be the acid. All right, this ammonium has extra hydrogens because it's positively charged. So it's considered as the acid because it can give the hydrogen to the carbonate. All right, so this is before it donates and this is after it donates. This is the acid, this is the base, and then you can just pick the other two are going to be the other pair. Okay, so let's take a look here. This is HCl and ammonium. Okay, so I'm already going to say that's the acid, that's the base, just because we know that HCl is the acid and ammonia is a base. Now let's see which ones are paired. Well, I know that one's going to be paired and I know that one's going to be paired. This one was, it donated its hydrogen and landed up being that. This one accepted the hydrogen, landed up being that from that. Okay, so this now becomes the acid and this one becomes the base. Acid, base, acid, base. Okay, they must, whatever you've linked, one is an acid, one is a base. Okay, let's take a look at this one. Again, look here. Fluoride doesn't have hydrogens to donate, so it has to accept. Okay, so this one has to be the acid. This one has to be the base. After it has accepted, and it's not always in this order, this one has now got HF, which makes that one the acid. And now this one automatically becomes the base. And so your conjugate acid-base pair is NH4 plus to NH3. And the other conjugate acid-base pair is Fe minus to HF. And you can see how this one has become the acid now, because it really could donate its hydrogen to that. And we know that hydrogen fluoride is an acid. Okay, what is the conjugate acid of? Now we've just got a single thing. So a conjugate acid, excuse me, is telling us that this is a base. If you're looking for the conjugate acid, it means that you start with a base. So base will accept a proton. So the conjugate acid will then have a proton. And there we go. All right, so that is the acid because it has the hydrogen. After it had been donated, it becomes the base. Let's take a look at this now. Water. What is the conjugate acid? Remember, if you're looking for the acid, the conjugate acid, that means you're starting with a base. So if this is the base, it will accept a hydrogen, and so we'll end up with a hydronium ion. Okay, what is the conjugate base of that? So if we're looking for the base, that means we've started with an acid, and we are giving it away, and so we have lost that, and we form an ion. Okay, or a charged particle. Water now, we're looking for the conjugate base, so it must be an acid where it donates its hydrogen, and once it's donated, it lands up with that. Remember, when it donates the hydrogen, it's donating a proton, which means that it becomes negatively charged. All right, I hope you understand, and please ask me if you're not sure. We can do a Google Meet if you need to, but what you can do is do exercise 13.1. I'm going to put it on WhatsApp if you don't mind. I've taken the photos and I'll just put them on WhatsApp when you're busy with this, and the memo. Okay, so I'm going to leave you now to try this for about a half an hour or so, and then you can do the task. Okay, you can start the task whenever you want. It's going to be ready by, I think, 11. I've put it on, but I can do it earlier if you want. Okay, so page 158, number 9. It's the same thing as what I'm doing on the task. Okay. And yeah, you can practice them, and you can even look at 13.1 to deal with some of all of this. Okay, and we'll post all the pages of acids and bases from their textbook, so you have the whole textbook. I have seen that Snapify is allowing you access. Maybe have a look. They're allowing access to textbooks, ebooks, until the end of the year. So maybe try and see if the IB textbook of this is available. That would be quite cool to have. And then at least Kayla and Robin, you guys can both get the textbook on at least virtually. So yeah. All right, guys, let me know how it's going now. Obviously, I did this the night before, so I'll speak to you tomorrow.